Okay, so then the next question is, when do you start counting things with heteroatoms in there? So a heteroatom means a non-carbon or hydrogen that's in there. And the answer is it depends, okay? When you think about these p orbitals that are open, and I'm sorry because my drawings are horrible here, only one p orbital can go in the same plane of those other p orbitals in that ring, right? In this case, we would have p orbitals coming up and down, and these pair of electrons are actually going away from that molecule. Now, that's actually happening here too, because this is sp2 hybridized, and the hydrogen would be coming out this way. But we can see pretty easily that there's 3 electron pairs that we're going to count in this, so that is an aromatic compound. This is also an aromatic compound, because we can only count one of those 2 electron pairs surrounding nitrogen, because only one of them can be in the same plane as the other ones. So we either count the double bond, which really is what we're counting, or we count the lone pairs, but we don't count both. So here we go, 2, 4, 6, or 1, 2, 3 electron pairs, and that's it, okay? So don't overcount. So let's look at how we can count some things. This would be 6 electrons, so 3 electrons pair, so that's aromatic. These are both 3 electron pairs, so they're aromatic. Now in this case, we're going to count 1 for this nitrogen, 2, 3, and you would count 1 for that oxygen. And so that would be anti-aromatic, okay? And, okay. Another way to look at aromaticity is through what's known as a frost circle or an inscribed polygon method. Most of the stuff that we look at in organic is dealing with things from a Vesper theory. This is using molecular orbital theory. And molecular orbital theory is very important because we need to have more than just one way to look at life and more than one way to look at chemistry. So just realize that this is something that tends to be on a lot of your tests that you may take after this course. So I'm trying to get into different schools and things like that. And it also is kind of something to really just look at how each of these individual p orbitals could give rise to the orbitals that put together the molecule. So that's what molecular orbital theory is doing, is it's saying, okay, here, you give a p orbital, 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 and now let's look at what we can do all together, okay? Now, the frost circle, what it's actually doing is it's trying to identify where these molecular orbital energy levels might be. And what we found, which is kind of neat, if you take your polygon and you put one of the pointy things, the vertice, downwards, then you just make that polygon like what you normally would, and if you were to take a circle on the outside, wherever that circle hits your vertices, that's an energy level of where the molecular orbitals will reside. So nitrogen's right here, boom, 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 boom. There's 5 energy levels for the 5 different vertices there, or the 5 different p orbitals are giving rise to 5 different molecular orbitals, and in reality that's what's happening. What we then do is we say, okay, let's draw a midpoint, a line in that circle that's sort of in the middle. Anything that comes in beneath that middle line is considered to be a bonding molecular orbital. So as you see here, those are bonding molecular orbitals. Anything that's above that line would be an anti-bonding molecular orbital, and anything that's on that line is a non-bonding molecular orbital. Excuse me. So if we take the 3 pairs of electrons that we have here, remember you're going to start from the bottom, 1, 2, and then you would do 1 here and 1 here before then putting down and down. Remember that from Gen Chem, right? So if you were to have more electrons, obviously this is good. We've got all of our bonding molecular orbitals filled, therefore this is a aromatic compound, it's happy. If we were to have more electrons, which you couldn't even have in this, if we were to have more electrons that we needed to count, they would start going up here. And they would enter the anti-bonding zone, which would mean that that would be an anti-aromatic compound, and that would not be good, right? So that's going to be a higher energy level thing. And if they go to the non-bonding, then that's just telling you that it's not aromatic. So let's look at something that's a little bit even simpler than that. And that is, if we start with this guy right here, and the first thing that we have to do is we have to rotate him to make sure that you have a vertice on the bottom, right? So that's 1, 2, 3. We have 4 electrons here, or 2 electron pairs, and it goes 1, 2, and then 1 in each of those. If you were to draw a circle, the midpoint would be right here through the middle of the triangle, right? Well, that means that we've reached anti-bonding orbitals up here, and that means that the compound is anti-aromatic. Now, hopefully you realize that from the previous rules, but if not, it's another way to look at things, and it's another way to confirm your hypothesis or confirm your thought process, shall we say. Thank you very much.